So thank you to the organizers for the workshop and thanks for the invitation to speak. My talk today is titled Bootstrapping the KLT Formula, and it's mostly based on this paper that I wrote with Henrietta Elvang, Callum Jones, and Aidan Hodashi, and Huanhang Chi. And I'll also say a few things about the massive double copy, which is based on a paper with Laura and Callum. So, okay. This workshop is called Rebuilding the Tower of Babel. So I felt like I had to make this little graphic that I'm quite proud of. And basically the Tower of Babel and different languages in which we speak about the double copy. And in this talk, I'll mostly be speaking in the language of KLT. But I will say that there are two sort of dialects in the KLT double copy language. One of them is the string theory KLT, and the other is the field theory KLT. And in this talk, I hope to be able to bridge the gap between these two dialects of the KLT double copy language. Okay. So just so that we are all thinking about the same things, I just want to make it clear that I'll be talking about on-shell scattering amplitudes only at tree level in 4 dimensions. And often they'll have color ordered external states, and those external states, if they carry any group structure, will be adjoint. And the main reason, I don't think I need to motivate it to this audience, but the main reason that I want to use scattering amplitudes is to understand some structure in the space of quantum field theories. That structure will be the double copy structure. But I really want to think of it as a map on the space of quantum field theories. And of course, scattering amplitudes are nice because you can check whether they come from a local unitary theory based on their analytic structure, a fact that we'll use a lot. And of course, they're gauge invariant. Okay. So the double copy, as I said, I'll be thinking about as this multiplicative map. And I want to think about it as theory A times theory B gives theory C. This has been shown to work in many different contexts. We will be thinking, as I said, about tree level. And the original example, of course, was Yang-Mills and Yang-Mills squares to gravity that's coupled to a dilaton and some two-form antisymmetric two-form. Okay. Now, this field theory example descends directly from the string theory Kawai, Lewin, and Tai KLT relations. So those relations were this really nice formula that expressed closed string scattering amplitudes in terms of sums of products of open string scattering amplitudes. Right? So this is the closed string amplitude. These are the open string amplitudes with various orderings of their external states. And this object over here is the KLT kernel, which in momentum space looks like this. And I just want to point out here that this is sign of something which is alpha prime times something else, right? So this is a full, if I Taylor expanded around alpha prime equals 0, this has all orders in alpha prime, right? This is a complete result in alpha prime. Okay, so when I said that Yang-Mills squared equals gravity descends from this relation, what I was talking about was if I take the field theory limit, meaning if I take alpha prime going to 0, if I look at that limit, then the open strings, the only mode that's left of the open strings is this spin 1 mode, massless spin 1 mode. And for the closed strings, similarly, it's the graviton and the dilaton and the B field. Good. So a lot of rich structure arises when you take the field theory limit of the KLT formula. And I think the first nicest one, in my opinion, is the BCJ color kinematic duality, right? Which we've talked a lot about over the course of this workshop. And one nice thing about color kinematic duality is that it works beyond tree level, and you can use it to construct loop level integrams. Also, and Callum talked about this a little bit before, it commutes very nicely with supersymmetry. In other words, if I look at this web of double copies that was first found in this paper by CHY, I can dress any of these with any amount of supersymmetry and this still goes through. So okay, we can all agree that in the field theory limit, there are some very, very rich and nice features that arise. But there are two things that we lose in the process of taking alpha prime to 0. So one of them is the fact that in the KLT formula, your external states were allowed to be any of the string resonances. So they were allowed to have mass. Once you take alpha prime to 0, you're strictly in the massless regime. The second is that you had an answer that was true to all orders in alpha prime. And of course, when you take the alpha prime goes to 0 limit, you only have leading order. So you have this situation where in field theory, you have no higher derivative corrections and no masses. Whereas in string theory, you have very carefully tuned alpha prime corrections, so not the most general ones, and an infinite tower of masses. And really what I'm interested in is the in-between region, right? So you want a KLT formula that can interpolate. It can have the most general higher derivative corrections, and it can have some number of masses, but not an infinite tower of masses. Okay, so these are sort of the questions that we want to answer in this talk. Is there a KLT formula that interpolates between these two extreme regimes? How does one walk around in the space of double copy maps rather than the space of theories that can be double copied? And once we have a way to do these things, how do we identify which points in this space correspond to string theory, and is there anything that makes those points special? So yeah, so as I said, these are the goals of the talk. Please feel free to stop me at any time and ask questions, but this is the plan. This is what we're going to be doing. Okay. So in particular, we will look for a KLT formula that includes effective field theories, effective operators. And then once we have that, we'll study leading order limits and locality. The prime example that I'll be talking about is Yang-Mills. So basically the Yang-Mills effective field theory and how it double copies to a gravity EFD. And I will at the end discuss how crucial it is, or whether or not it is crucial, to always have a trivalent graph decomposition. And we'll talk more about what exactly I mean by that. Okay. So the starting point will be the KLT algebra. So this is the KLT formula again for in the field theory limit. For those of you who are not familiar, this is telling you that you take an amplitude of theory A, take an amplitude of theory B, sum over some orderings of these external states with the KLT kernel, and that gives you the amplitude of a theory C, and these are the theories over here. Now, you'll notice that this theory over here, phi cubed, which is the bi-adjoint, the cubic bi-adjoint scalar theory, which is a theory with this interaction. So these scalars are bi-adjoint in that they carry two color indices, both adjoint, and it's a cubic interaction, and they're massless. So clearly the bi-adjoint scalar theory acts as an identity in this KLT algebra, and I use the word algebra rather loosely. I basically mean this set of multiplicative relations. Okay, so the bi-adjoint scalar theory is special because it's the identity of the double copy. Now I want to flip that around and say, if I want to generalize the KLT formula, why don't I start with the assumption that all generalizations of the KLT double copy must have an identity element? And having an identity element means you have a theory that satisfies relations like 1 times A is A and 1 times 1 is 1, right? Good. So let's look at let's look at this relation first. 1 times A is A. What does that tell you? So written out, this is what 1 times A is A means. And you'll notice that because A has some color structure, it has to have an ordering. And because the KLT formula sums over orderings, this forces the identity element to be associated with 2 orderings rather than 1. So you'll see over here that I have 2 orderings in the KLT for the identity element, right? So it tells you basically that the identity theory must be bi-adjoint. The second thing you can read off of this formula is, in order for the spin to work out correctly on either side of this formula, the states of M have to be scalar states, right? So in order for me to start with spin 1 states on the right and get spin 1 states on the left, the identity theory or the identity element must be a bi-adjoint scalar theory. So that comes just out of assuming that the KLT double copy has an identity element. Good. All right. So of course, if it's an identity, it also needs to satisfy 1 times 1 is 1. Again, write that out in completion. And you'll find that this formula takes this form, and I can think of each of these as being matrices of scattering amplitudes, where the rows and columns of the matrices are orderings of these external states, right? So I can just treat these as matrices. I can multiply the inverses on this side, and that gives me this formula over here, which has been recognized before in multiple papers, in particular by Sebastian Mizera, in a paper from, I want to say 2014, but actually I'm not sure. But this is important to us because this is telling us that a double copy is defined by its identity element, meaning that the set of identity elements is the set of bi-adjoint scalar theories, which is the set of double copies. So I can span the space of double copies by spanning the space of bi-adjoint scalar theories. Now, once we have that, we can also use the fact that there are various different bases of orderings that we could have used, and the basis independence of the KLT formula allows us to sort of extract more juice out of these identity expressions. In particular, it gives you the right and left BCJ relations, which I'm basically calling any linear relation between amplitudes of the same theory a BCJ relation. Good. And only theories that satisfy these BCJ relations can then be double copied. And finally, basis independence of this relation is what I'm going to call the KLT Bootstrap equation. Okay, so why am I calling it that? It's because if you look at this equation, it only involves amplitudes of the bi-adjoint scalar theory. So this is a self-consistency condition that has to be satisfied by any zeroth copy. Okay, so to summarize what I just said, there are these 3 relations that make up the KLT algebra. The first determines the space of identity elements. And I already argued that the space of identities is the same as the space of possible double copy relations. The second relation over here determines what kinds of theories we can double copy. And the last one determines what we can calculate using such a double copy, right? So said quickly, the first determines zeroth copies, the second single copies, and the final double copy. In practice, what does this mean? It means that I can start with a matrix of bi-adjoint scalar amplitudes. These don't have to be cubic, they don't have to be leading order, they're just some theory of a bi-adjoint scalar. I take the inverse of a full rank submatrix to construct a KLT kernel. I enforce that such a KLT kernel must satisfy the KLT bootstrap equations. I then check that my amplitude satisfy the corresponding BCJ relations, and finally I can use the KLT formula to construct a double copy. Okay, so these were a lot of words and a lot of formal setup. So let's see how this works in the usual case in the field theory leading order BCJ. Okay. So there you have the bi-adjoint that you're dealing with. The identity element that you're dealing with is this theory over here. And this theory has these doubly color ordered tree amplitudes that look like this. So clearly, because of the cyclicity of the traces, there are n-1 factorial squared number of amplitudes sitting in this matrix over here. And the KLT bootstrap equation basically gives you further relations between these n-1 factorial squared amplitudes. It gives you actually two kinds of relations. One are known as the Kleist-Coif relations, which are relations between linear relations between amplitudes with different orderings in theories that have FABC color structures discovered by Kleist and Coif. And the other are what we normally would call the BCJ relation. The upshot of this is that you find that the rank is n-3 factorial. Okay, so at 4 point, what does that mean? It means rank 1. So at 4 point, you have these kinds of scattering amplitudes over here. And because this matrix of amplitudes has rank 1, I can choose, for example, this basis 1, 2, 4, 3, and 1, 2, 3, 4, and just take this element, invert it, and that gives me the KLT kernel. And choosing different bases of orderings will then give me consistency conditions like this. And these are just BCJ relations. And I can then write down the double copy. Okay, so this is kind of what I want to do, except I want to change what I mean by the identity. Before I do that, let's notice why changing the identity might be scary. And that's because of locality. So locality is very carefully tuned in this example. If you look at this formula, this amplitude could have had a pole in S, right? Which means that the square of the amplitude could have been 1 over S squared. And unless my KLT kernel or the identity element created a KLT kernel with a factor of S in the numerator, I could not have canceled this to form something local with no double poles on the left side. Good. So we should be careful when messing with this element over here, this identity element over here. And we've conjectured and we've checked this up to 6 points for the higher derivative stuff and up to 5 points for the massive stuff, that if you ensure that your matrix of bi-adjoint scalar amplitudes has rank n-3 factorial, then you always get a local double copy. So this is conjectural, and I'll talk about why you might want to make such a conjecture, but for the time being, let's take this as one of the inputs. Good. So, all right, let's start doing what I promised, which is to add effective operators to the KLT kernel. Now, I do this in the regular way. I say that my total amplitude is some leading order stuff plus subleading stuff. And I enforce that this full matrix of amplitudes has rank n-3 factorial. I impose the KLT bootstrap for all choices of bases, and that selects a particular set of high derivative corrections that I'm allowed to have. And actually, assuming that basically when the EFT cutoff in this theory goes to infinity, I get back the leading order, assuming that this is true. The high derivative corrections cannot change the leading order rank without introducing bad scaling with lambda in the double copy theory. Okay. I also want to emphasize that we are allowing here at subleading order different color structures. So because of the fact that the Kleist-Coif relations are only true if you have FABCs, and we want to include for the high derivative corrections other kinds of color structures, we want to start with a basis of n minus 1 factorial rather than n minus 2 factorial. So we start with a bigger basis basically so that we allow these different color structures. Good. So what does this bigger basis look like? At 4 point, it means that you have a 6 cross 6 matrix, which once you take into account cyclicity and momentum relabeling, it reduces to these three functions. Now, applying the KLT bootstrap equations on these three independent functions, we find that they are not independent. So F6 and F1 are both determined in terms of F2, and F2 satisfies this sort of self-consistency, has to satisfy the self-consistency condition. Excuse me. Yeah. So what kinds of stuff actually satisfies such a condition? Well, we know one example, which is string theory. So the string theory KLT has to satisfy those consistency conditions. So what do I mean by that? I mean that if you take F2 equals this, which is exactly what it is for the string KLT, it will satisfy this equation over here. Furthermore, you can think of this F2 as being as coming from some bi-adjoint scalar EFT resummed, right? So you can just expand this in alpha prime around alpha prime equals 0, and this just looks like bi-adjoint scalar with a bunch of high derivative corrections at 4 point. Good. Another possible solution is actually anything of this form over here. Now, this is interesting because it means that not all solutions correspond to sensible field theories. So just because I can satisfy this condition over here doesn't mean that F2 will correspond to a 4-point scattering amplitude of a sensible bi-adjoint scalar theory. And this example over here is I mean, this F2 function over here is a good example of such a thing. And actually, the string theory example itself is a pretty good example because this, well, 1 over sine is not an amplitude. It doesn't have the right pole structure. Around alpha prime equals 0, it does, but once resummed it doesn't. Okay, good. So let's find the most general answer. So the most general answer, to find the most general answer, we start with an ansatz, which is this over here, where we introduce these Wilson coefficients AKR. We then solve the bootstrap equations that gets rid of some of the coefficients. So you'll notice, for example, that A21 and A22 are removed. And of course, as one would expect, this is more general than the string theory result because the string theory result is the special assignment of the AKR coefficients. Good. So this is now our 4-point generalized KLT kernel, which corresponds to an identity theory with such a Lagrangian, for those of you who like Lagrangians more. Good. So what can we double copy with this setup? So let's start at 3 point. At 3 point, I want to understand what I can double copy, what I can add to Yang-Mills and then double copy. In this case, the BCJ relations actually just boil down to antisymmetry of identical states. And so you have exactly two possibilities. One is the usual Yang-Mills coupling, and one is the F-cubed coupling. So some of you might be used to throwing away the F-cubed coupling because it's non-supersymmetrizable, but in this case, we want to be as general as possible, so we include it. Moving on to 4 point, we know now what the poles need to look like because we know the allowed 3-point interaction. So we can write down this ansatz, where again, I've introduced some Wilson coefficients in the Yang-Mills EFT. And we can solve the BCJ relations. And you can see that actually the BCJ relations get rid of a lot of the coefficients. Basically, it only starts at k equals 3 over here. And all the h coefficients are determined in terms of the E coefficients. Another thing you'll notice about the final answer is already at the first subleading order, lambda to the fourth, you get a contribution from these coefficients over here, which, as I'll remind you, were part of the KLT, the generalized KLT corner, right? So this is a new operator in the single copy theory that you're allowed to double copy only because you did this generalization of your KLT corner. Good. So now I can, of course, use this Yang-Mills EFT to double copy to gravity EFT, and you get this answer over here. So a few things about this. The first pole is the usual gravity pole. The second is due to the exchange of a dilaton. And this contribution over here, as you can see, is a mix of contributions from the KLT kernel and the Yang-Mills EFT coefficients. And I just want to point out that clearly you can shift information from the KLT kernel into the Yang-Mills EFT and vice versa. So what does this mean? It means that our 4-point results are suggestive of the fact that while generalizing the KLT allows you to double copy more kinds of things, so it enhances the space of your single copies, the final space of amplitudes that you land in after doing the double copy is the same. So it is suggestive of this. So let's see if this continues at 5 point. So, okay, sorry. Before that, this is just a summary of what I just said. This is the total number of operators you could possibly write down, the number of operators allowed, which are compatible by the generalized BCJ, the string BCJ, and the cubic Bi-adjoint scalar. And so this clearly shows you that there are more things you can double copy now that you have a generalized kernel. And again, as I said, once you do the double copy, you get the same operators. So let's see if that continues at 5 points. So at 5 point, you have now a 24 cross 24 matrix, which has 8 independent functions, which are called G1 through G8. And you can construct the local ansatz for each of these. And you'll notice that each local ansatz will now have input from the 4-point amplitudes that we figured out when we did the 4-point KLT bootstrap. Okay. Now, solving again for 1 times 1 equals 1, we get answers such as this one over here. And you'll notice actually that up to this order, which is lambda to the 6, there are no independent coefficients at 5 point. Now, this is kind of just an accident of lower orders. At higher orders, you do get independent 5-point coefficients. But these are all the coefficients in red. These are all 4-point coefficients. Okay, so now that we have this, we can find BCJ compatible corrections to Yang-Mills and then double copy them. And this is what we find. Again, so this is in the self-dual sector, I should say. But we find that there are more things we can double copy with the generalized kernel. And we find that once we do the double copy, it is the same corrections that are produced as in all cases. So this enhances the space of single copies, but not the space of double copies. So just to give you a sense of the scope of these results, this is a very general sort of procedure. And so you can apply it to any of the theories in this little table over here. In particular, one thing that I was interested in was doing this for Born-Infeld theory. So Henrietta Elvang, Marius Hadjiantonis, Callum Jones, and I spent some time trying to understand electromagnetic duality in Born-Infeld theories. And we found that the primary thing we were trying to understand is whether or not electromagnetic duality is anomalous in one loop in Born-Infeld. And our calculation of the one loop result was in a regularization scheme that led to a local counter term needing to be added to restore the duality that wasn't produced by the double copy. And so one of the motivations actually of doing this high derivative double copy for me was to see whether you could generalize the double copy to include EFTs to see whether such a counter term would be produced or not. And it's interesting that because of the fact that the double copy space is actually not enhanced, you don't, I mean, changing your double copy procedure isn't going to change what kinds of things you can add to bond theory. Good. Okay. So all of this that I talked about just now was based on the fact that we assumed minimal rank, meaning that endpoint amplitudes have n minus 3 factorial independent orderings. Now, or in the case of bi-adjoint scalar, n minus 3 factorial squared independent orderings. And this was inherent already in the fact that the KLT bootstrap equation 1 times 1 equals 1, I wrote in terms of this, which already assumed that the rank was 1 for 4-point. So I think now I think it's my responsibility to tell you why I think we need minimal rank, or rather what goes wrong if you violate minimal rank. And there's two ways of doing it. One, you can violate it at subleading order, and two, you can violate it at leading order. And I'll go through both of these scenarios, and hopefully by the end, you'll be convinced that minimal rank is a good idea in the most generic cases. So let's see what I mean by that. Good. So at subleading order, if I wanted to change the rank of my identity element or my bi-adjoint scalar theory, I could do something like this. So here I've added a 4-point coupling. It involves these DABCDs, which are these symmetric combinations of traces of symmetric combinations of the generators. Good. So this modifies the amplitudes in my theory in the following way. So it gives me these kinds of 4-point amplitudes. Now, what could possibly go wrong if I did such a modification? Now, I already hinted at the fact that what goes wrong is locality. So let's see why locality would be affected by changing the identity element. So this basically happens because the KLT kernel is an inverse of a matrix, right? And so when you invert a matrix, you're doing 1 over the determinant times a matrix of cofactors. Now, cofactors are just products of sums and differences of products of matrix elements. And in this case, each of the matrix elements is a physical scattering amplitude. So sums and differences of products of scattering amplitudes can never have any extra poles or any bad poles in them. They can only have poles at physical locations. So the only source of a bad singularity or a bad pole in the KLT kernel is zeros of this determinant, right? So all we need to do is look at the determinant. So let's look at the determinant. So I'll remind you, we're looking at the determinant in the case of such a deformation, and we find that it looks like this. So it has a 0 at s equals minus 2t, which is not a physical location for a singularity. Good. So what does this mean? It means that naive deformations that change the rank of bi-adjoint scalar theory at subleading order will generically lead to non-physical singularities in the KLT kernel. So what happens if I try and do something similar, except at leading order instead? So now I'm going to allow my bi-adjoint scalar theory to not just be cubic bi-adjoint, the usual cubic FABC bi-adjoint scalar theory. It can be something else. And now in this case, so for example, the most naive thing is to add such a coupling to cubic bi-adjoint scalar. So this now involves DABCs instead of FABCs. So DABCs are just 3-point versions of this. So T, A, T, B, T, C, where P and C are symmetrized over. So once I add such a thing, and I use that as my 0th copy at leading order, then these are my amplitudes at leading order. right? So yeah, these are my amplitudes with leading order. You'll note that lambda 3 doesn't change sign, and that's because DABC is symmetric in ABC. Now, if I use such a theory to construct the 5-point KLT kernel, I find that the 5-point kernel has a variety of matrix ranks. Now, to remind you, rank 2 is minimal rank, it's n minus 3 factorial. And that happens, of course, when I set this to 0 and I'm in the usual case of cubic bi-adjoint, and there are no spurious poles in the determinant in that case. In all other cases, I get non-minimal rank, and I do get spurious poles in the determinant. Okay, so this should tempt you to say that when I go to non-minimal rank, either at leading or subleading order, I end up with spurious poles in the KLT kernel. And so my double copy is bound to be non-physical, and I should throw these things away and not consider them as zeroth copies. And unfortunately, there is something that prevents you from being able to make that reverse implication. And that is that you can still evade bad poles. And unfortunately, I couldn't be at Mariana's talk this earlier today because of the time zone and the time difference. But I think she must have told you more about how to evade these spurious singularities. And I'll give you a very trivial example as well, which is in the case that we were studying with this lambda 3 coupling, you can still double copy a single scalar theory that looks like this, and it'll give you a perfectly reasonable local double copy, and the final double copy that you get will be phi cubed. Okay, and you can play this game where instead of doing DABC phi phi phi, you can do DABC D phi 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 phi. So basically the quartic version of that deformation. And again, you'll get spurious poles at 8 point, but those spurious poles will cancel and you'll get a perfectly local double copy if you are double copying this single color scalar theory, and it'll double copy to 5, 4. So there are a couple of trivial examples that prevent you from doing the reverse implication, that any local double copy must come from a minimal rank KLT kernel. And I think actually it's very interesting to understand all of the cases where these cancellations occur and where you can get a local double copy despite not being minimal rank. Okay, good. Okay, so just to give you one last example of the scope of the KLT Bootstrap, you can also use this kind of procedure of starting with the KLT algebra and demanding consistency to construct a massive double copy. So instead of higher derivative deformations of bi-adjoint scalar, if I instead considered a massive deformation of bi-adjoint scalar, where I basically decorated all of the bi-adjoint legs with different masses, I could then calculate again the matrix of bi-adjoint scalar amplitudes. The rank of that matrix would be 2. So to reduce it to minimal rank, I would have to set the determinant to 0. And that will give me a condition that has to be satisfied by the masses in that theory, which we call the spectral condition in this paper with Callum and Laura. And there was some associated massive BCJ relation. So this also, I mean, though we didn't realize it at the time, this is the same exact procedure where you start with this identity element and modify it to get a modified double copy. And I'd just like to mention that such spectral conditions have been seen to be satisfied by Kaluza-Klein reductions. And this was explored more in a nice paper by Momeni, Rubutis, and Tolly. Okay, great. So we saw basically, I hope I motivated that one nice way of understanding the space of double copies is via the identity elements or the bi-adjoint scalar theories. There's still a lot of open questions. One of them that I'm interested in is what can you do other than the FABC cubic bi-adjoint? What else can I do? And I showed you examples with DABC, which sort of worked in some examples, but it's unclear to me how much that generalizes and how, basically how special is bi-adjoint scalar, the FABC cubic bi-adjoint scalar. The second is there's been work by Carrasco, Rodina, Yin, and Zekiolu, where they have a way of writing down effective field theories and enumerating what kinds of operators you can have in them via BCJ color kinematics. And it would be interesting to see exactly how our procedure maps onto theirs. At 4-point, it is quite simple to see that the single copy amplitudes that they find and the single copy amplitudes that we find are the same, which means there's got to be some equivalence of the two prescriptions. So yeah, it'll be interesting to see how that works at 5-point and beyond. Another thing is related to fundamental matter. So all I talked about over here was adjoint matter. So fundamental matter would be interesting to study. I also think when it comes to the massive double copy, in order to really build something that interpolates between field theory and string theory, it would be nice to see something that is not Kaluza-Klein. So something that doesn't have only one mass that runs in each channel. Because again, Kaluza-Klein is interesting, but it is an infinite tower of masses. And it would be interesting to see if you could instead have some truncated set of masses in a double copy. And finally, there's this thing that Calum talked about, which is to understand really what it means or whether there are generalizations of the double copy that can now include massive supersymmetric theories, now that there's so much nice formalisms and so much nice language in which we can talk about massive supersymmetric theories. Okay, so this is a summary, and thank you for listening, and I'm happy to take questions.
Thank you for the very nice talk, Shruti. Are there any questions?
Yes, could I ask a quick question?
Yeah.
Yeah, so about the availability of, yes, so you've identified this almost possible space of possible KLT kernels. And it's known that at least in some cases, the regular field theory BCJ kernel can be realized in terms of, ambitwist of strings and similar formalisms. Do you think it's possible that, how much of this space of possible KLT kernels do you think would be realizable as some versions of string-like things?
Good. So, I mean, I guess one easy answer is that there are two limits in which you can do that. One is the full KLT limit, where it's the actual string theory, and one is the leading order, where it's the CHY formalism.
Right.
As I said, I've not looked into this carefully, but I do wonder if there is something you can do where so in CHY, you could do something which is trivial, which is you take the things that you're double copying and then you add stuff to that. But that's not quite what we want to do. We want to change the identity element. So you want to change what the CHY formula is itself. I'm not entirely sure how you would go about doing that, and whether that corresponds to looking at like some kind of effective ambitwisted operators. But I think it's an interesting question. I just haven't looked at it yet.
I see. Thank you.
Okay, any last questions?
JJ has one.
I've got a last question. Hi, thanks for a lovely talk, Shruti. Can I ask you a question about the operator you found at one loop, the counter term you needed to make DBI VA self-dual at one loop?
Yeah. So, I mean, obviously it's not here, but it's
Right.
right. It's the one that sits between lambda squared and lambda 6. So it's at 1 over lambda to the 4th, and it's as far as, yeah, I should have written it down, but I think there's only one thing you can write down at that order that has the right symmetry. So I mean, that has both symmetry and the right little group that is local. And yeah, so if you write that down, that's the counter term.
And so were you able to recover this with your approach?
No, but I don't think so that doesn't necessarily mean it's the end for electromagnetic duality. It just means that the regularization scheme that we used when we did the integral wasn't double copy compatible, I think.
Good, thank you.